Hello everyone. Let's continue with lecture number 2, which is about probability distribution. Okay, when we talk about constants, obviously it means some values like 2, 3, and so on. And when we talk about variables, it means that it can take different values. Different constant can be assigned to variables, like for example, x, y, and each one of them, obviously they can take different values. And for random variables, what about them? It means that if you consider capital X as a random variable, then it can take also values, but these values are random. So for example, x equal to 2, x equal to 3, and these numbers can be taken randomly. Like for example, if you throw a die, then in that case, it can get values from 1 to 6 randomly. So that's the definition of random variables. And usually for discrete case, we show them like this. And we say probability of a random variable to be equal to a random value. And also we can define x's as like events and say, for example, x is the event of number of heads, and x could be even continuous like this. But whenever this is the case, we should define it differently, just rather than showing it point-wise, because if you show it point-wise, it is equal to 0 right away, and we will talk about the differences. Okay, now let's see what's the difference between discrete distribution and continuous distribution. There are so many differences, so we should be careful that the distribution that we are talking about, whether this is discrete or continuous, and calculate the probabilities accordingly. And what do we mean by distribution at the beginning? Because when we talk about data, and what is data, by the way? Why not? Let's talk about it. So data is the raw information. It means that some values that you have which are not processed, like for example, the height of students in a class, then these are data. And what we get from this data as an information, then we need to analyze this data, or at least summarize them to get some information. So those values could be named as data. Now, here we should consider the distribution of them to say these data, do they follow a specific distribution? For example, does it have such a shape or not? Or for example, here we understand that point-wise it looks like this, and it is close to a type of distribution which is known. If that's the case, usually they name those famous distributions. And when we talk about, for example, binomial, Poisson distribution, or normal distribution, then they are famous because most of the data actually follows such trend. And now here from the beginning, we should distinguish between them. To know, for example, if they are discrete, then how can we calculate the probabilities corresponding to them? Now, in the first one on the left side, you can see this is a discrete distribution. It means that all the values related to probabilities, which are between 0 and 1 for sure. So the maximum value it can get should be 1. Then all of them can be calculated point-wise. It means that this point, and so on. There is no probability between them. It means that this is 0. Okay, so it means that if I wanted to consider from minus infinity to plus infinity, for all of them, I should show the points like here, like 0. That's why they usually don't show it. So there are gaps between these points, and the probability is 0 between them. But in case of continuous distribution, this is totally different because you should consider the area under the curve. Like, for example, what's the probability of this area? That's how we deal with continuous distribution. If you consider only one point, like discrete distribution, like to say what's the probability of exactly one, it means that you are talking about a line under the curve. So what's the probability of that? It will be 1 point over infinite number of points, which is approximately 0. That's why whenever you hear about pointwise probability in continuous distribution, right away you understand this is equal to 1. So for example, in discrete distribution, if we ask you what's the probability of x equal to 3, then by looking at the corresponding probability, you can say what's the final answer, which is here 0.217. But here, if I ask you what's the probability of x equal to 1, as soon as you see equality for a continuous distribution, it's obvious that this is 0. We are talking about a line, not the area. So whenever you want to have some sort of probability under the curve, then you should have an area. So whenever you have an area, you can calculate the probability. Otherwise, this is equal to 0. So these things we should be careful about. Also about discrete distribution, that there are some places that you should consider them 0. As I said, they have gaps between them. So for example, the probability of x equal to 1.5. What's the probability of that? Okay, as you can see, between 1 and 2, we don't have any points here which contains probability. There are gaps between them. So whatever we ask between 1 and 2, right away you could say this is equal to 0 as well. Also, when we are dealing with probabilities regarding distributions, we are interested in cumulative probability. What do we mean by that? It means that, for example, x less than equal to. What's the probability that x would be less than or equal to? So in that scenario, you should get the summation of whatever probability you will find from 2 and whatever is less than that. So what's the probability of x less than or equal to? This is equal to probability of x equal to 0 plus x equal to 1 plus probability of x equal to 2, and the summation of them will be the final answer. And we can do the same exactly for continuous distribution. So in discrete distributions, we are dealing with summation of points. But when we talk about cumulative version of these probabilities in continuous distribution, we are talking about integral. Okay, so when you want to calculate the areas under the curve, you should use integral, which you already know from calculus. So let's go through probability mass function and cumulative distribution function. As I mentioned, we are interested to consider them pointwise or in cumulative versions. So here, as you can see, when you consider it pointwise, it means that this is a probability mass function for discrete distributions. And whenever you consider it like cumulative format, then in that case, we call them CDF or cumulative distribution function like this. So in the lowercase part, you can just simply consider value. In the previous slide, I gave you one example, for example, x equal to 2. So this part is the random variable that you show it like this, and this part is the value that you assign to it. And in terms of cumulative, as you can see, you can use less than or equal. And whenever you have two variables, then in that case, you can show it like this and find the cumulative version of the probability like that, and I will show you also in an example to see how easily we can deal with that. Now, an example related to probability distributions. So let's say, for example, I want to give an example about PMF. And also through that, I will show you also how to deal with the cumulative one. This is a very simple example. Let's say X is a random variable, and I define it as the number of cats in a house. So people tend to have pets, and some of them prefer cats. And let's say they can either have 1, 0, 1, 2, and more in their houses. For simplicity, let's say nobody keeps more than 2, but as you know, this is not the case. Just I want you guys not to be confused about the signs from the beginning. So let's say the number of cats they can have in their houses are either 0, 1, 2. Now, what's the probability of having, for example, number of cats to be equal to any of these numbers? So I showed this one by a lowercase x. This is capital X, this is lowercase x. So it can, each one of them can have some probabilities. Like for example, for having 0 cats in a house, then we could say the probability of x equal to 0 is 50%. Okay, so half of the houses, they don't have any cats in them. And for 1, let's say this is 20%, and for 2, this is 30%. Now, what I want to show you guys in this easy example is to look at this one, pay attention and see what do we mean by probability distribution. So already you understood about the notations and why I use them like this. And the thing you should be careful about to check whether this is a probability distribution or not is that each one of these values, they should be between 0 and 1. They can also get 0 and 1 themselves, as we explained about probabilities. So why is that? Because each one of them is a probability anyway. So each one of them, we should be careful that this is between 0 and 1 inclusive. The second condition that we should check is that the summation of them should be equal to 1. Now, the rules related to probability that I mentioned before make sense now. Do you remember we said summation of the probabilities, and then we made it equal to 1 in one of the rules related to probability. Now it makes sense here. So whenever we talk about probability distribution, you should be careful that the summation of these probabilities at the end should be equal to 1. And the other thing that you should notice is that each one of them are disjoint. It means that it's not possible to have, for example, 0 and 1 cat at the same time in a house, right? It doesn't make any sense. So all of them are disjoint. That's why the summation could be 1 and there's no intersection between them. And in case of continuous distribution, we define them like probability density function, PDF, and also for cumulative formats, we say CDF, which has the same initials as the discrete version, and we call it cumulative distribution function. And as you can see here, we use integral instead of summation. So in case of discrete one, we use summation. In case of continuous one, we use integrals. And it starts from minus infinity to x, the value that we assigned here inside this function. And it can even go until plus infinity. Now, when it goes there, what should be the answer? The answer should be 1, and I will talk about it later. So what about having 2 variables? Then in that case, we can define 2 distributions as joint distributions at the same time. So in that case, it's interesting to know whether these two distributions are independent or not. Also, we will check them. And you see here, we talk about marginal distribution. So you remember I talked about marginal probabilities. So it's very similar to this one, and I will talk about it now. Okay, and about joint PMF for discrete one, you can see that I can define it like the intersection of the probability of each part, and I will show you in the example to make sense about it. And as you can see, for summation of both x and y for the joint distribution, it should be 1 if I consider all x's and all y's. And it was exactly the same reason for the continuous one when I consider integral from minus infinity to plus infinity, which we will practice together. And the joint distribution has all the information about the random variables, yes, and marginal probabilities can be computed. And I will show you also about that in the next slide. Now here you can see that the probability for each variable, and here we consider each distribution, can be also calculated using the joint distribution. And when you want to do that, you should fix it on one variable, let's say for y equal to 0, and consider it based on the values that x can have. This slide can be confusing now, but as soon as I show you the example, you will see how easy it is. So when I will give you the example, then return back to the slide to know what we are talking about. Because here you can see I'm interested only in marginal distribution of x, and I can calculate it based on the joint distribution by fixating it on y, which is the other distribution. And in case of independent random variables, this is very similar to independent events. So in that case, you can easily find it by multiplication of these two distributions, and the joint distribution can be easily found. But this is not always the case, because usually the distributions are not independent. So in that case, you cannot easily find it like this. And for them, we should give you the complete table in order to know how to find the joint one and how to find the marginal ones. Okay, now take a look at this table and try to understand what they mean, this information. Now here, as you can see, we have the joint distribution, and in the marginal parts, you can see marginal distribution. Okay, so here the information is given to us, so we don't need to calculate them. It's very easy. So this is an easy example. Usually in our daily calculation, we don't see such things. But anyway, just to learn about it, then we will give you more complicated examples. But for the time being, to understand about the joint discrete distribution. Now we are talking about discrete ones, not the continuous one, which we will talk about 2 weeks later. Now, in this example, you can see this joint distribution is given based on x and y. And each one of them, they can have different values. Like for y, it can get 0, 1, 2, 3, and for x, 0 and 1. Now, what are these values here? These ones are probabilities, okay? So each one of them should be between 0 and 1. Let's return back to the simple example. Here you see all of them were related to x. Now just one variable, one distribution. But here we have joint distribution. It means that we are dealing with two variables, x and y. But they are the same. The logic is the same. I mean, again, all these cells can take values between 0 and 1 because all of them should be probability, and their summation should be 1. You see, the summation should be 1. If you get the addition of all these probabilities, it should be 1. Now, how to find marginal distribution from this joint distribution? For example, let's say I'm interested to find about distribution of x. So in that case, I can show it like this, and to be more accurate, you can also show it like this to be similar to our previous example. To do that, you should fix it on one variable. Like for example, here, let's consider for x equal to 0. Then I get the summation for y, you see? So whenever you want to find what's the probability of x equal to 0, then you should calculate the summation based on y on your joint distribution. So here you should consider the joint distribution. You remember when I use this notation, it means that fill it yourself, okay? You shouldn't use this one. Okay, so the summation of these ones, because I fixed that on x equal to 0, and I could calculate it with this one, which is 50%. So you see, this slide now makes more sense. I'm talking about the intersection here. So these cells, each one of them, they are representing of intersection. What does it mean? For example, what is this cell? This is probability of x equal to 0, and at the same time y equal to 1. You see? So I can show each one of them as intersection, and to be more accurate, you can even use this notation. But usually they show it with comma to show at the same time they should happen like a pair. So here for x equal to 0, I could find it like this. For x equal to 1, again, I should find the summation of these cells, and it should be 50%. And the summation of these two together, it should be 1. Why is that? Because px itself is a probability distribution. So if you consider only this table, this is a probability distribution. And of course, by considering this part. So for 0, this is 50%. For 1, this is 50%. And this is equal to 1 as the summation. So this is very similar to what we talked about here. You see? So now instead of 0, 1, 2, I have only 0 and 1. And each one of these probabilities are equal to 50%. And their summation is equal to 1. So that's how you can find marginal probabilities using the information related to joint probability. And in the same example, I want to talk about independency of distributions. So take a look at this table. How can you check about their independency, whether x and y are two independent distributions? Think about it a little. Okay, to do that, let's check at the this formula. This one actually is better shown for continuous one. For the discrete one, just interchange the place with the discrete format. So you can show everything like this, for example, okay? So usually for continuous version, we show it by f because they are density function. But time to time, if you see, for example, they write fx and fx is equal to this one, don't be surprised because it can be used as well. Okay, so to check whether x and y are independent distributions, you should check for each one of the cells that whether this value is equal to multiplication of the marginal ones. So what are you doing here? You are considering the probability of x equal to 0 and y equal to 0, and you are checking whether is this equal to the multiplication of the marginal ones or not. Okay, so from here you should know about the differences between these two sides. The left one of the equality means the joint probability. The other part means the multiplication of the marginal probabilities. That's why I'm calling them marginal probabilities. Now it makes sense. And the whole thing, considering this part and this part together, we call it probability distribution, and for y we can do the same. Okay, so for each one of the cells we should check it. For example, for the first one, I check and I understand 20 is equal to 50 multiplied 40. So that one is okay. But again, for other cells, I should check. Even if one of them doesn't make sense, if it's not equal to each other, so it means that these two events are not independent. And that's why we are looking for a counterexample. As soon as you find one of them not to be equal to the marginals, then you say, okay, then these two distributions are not independent. For example, this one, the marginal of x and y. If you multiply them together, 15%, which is not equal to 20%, so you would say these two distributions are not independent. And usually you can say they are dependent instead of that. Okay, what about the term expected value, which is very important for statistics? Now take a look at this slide. Expected value is related to the central criteria. What do I mean by that? If I want to simply describe it, it can be related to average of numbers, and we call it in a statistic mean of that attribute, and we call it by we show it by expected value of x, and you can also denote it by using mu. And here for discrete one you use summation, obviously, and for continuous one you use integral. What is this part? This is actually the probability distribution that we have shown you before. So as you can see, instead of fx, I can use this one. Capital X on the left side and lowercase on the right side. Now, here we multiply it by x and get the summation. What is x? Is the value that x can get. Now, in our example, I can easily show you what it means. Let's say I'm interested to calculate expected value of x. Then in that scenario, I should consider sigma, and here I should have x, and here I should have capital X equal to lower x. And this lower x that you can see here, this is exactly the same as this one, okay? And this sigma can get its value for x from 0 to 1. Yes? So let me at least for the first time write the whole formula so that you can see how it's done. We will practice it, of course, in our tutorial more. But here it means that you can write what are the possible values, 0 and 1. So starting from 0, multiplying by probability of x equal to 0. What is the probability of x equal to 0? 50%, right? plus, because we are dealing with summation, okay? So 1 multiply the probability of x equal to 1. And sorry for the mess because I'm trying to do it with the mouse. Okay, so what it means, now here I can write it more clearly. 0 multiply 50% plus 1 multiply 50%. So here this is 1, this one x equal to 1, which is 50%. So what's the final answer? This is 50%. This is the expected value that you can find for x distribution. And you can do exactly the same with y. So for y, the values can be 0, 1, 2, 3. And we get the summation by changing the values of x here. So the summation should be go through x, and we should consider, of course, the joint distribution. So exactly the same procedure for y, but consider the columns instead of the row, okay? And now here it's already calculated about the marginal one. So the only values that you need are these ones, and based on the values that y can get, see? So we will practice it neatly in our tutorial. This is just for your knowledge that what do we mean by probability distribution, and later we will practice again in our tutorial. So for continuous and discrete case, you can see that the only difference is sigma and integral, because here we are dealing with points and here we are dealing with areas under the curves. And what if I'm interested to calculate, for example, x power 2, expected value of x power 2, not only ex. So for calculating ex, we used x to multiply it to the probability distribution. Now, instead of x, the only thing you need to do is just to replace it by x power 2. That's it. So you see, it can be easily done because you already know about the general format. Okay, now take a look at this slide. This slide can be very useful for calculating expected values when we are dealing with more than one variables. So here, as you can see, the multiplication can get out of the parentheses. So it means that if you have expected value of cx, you are allowed to calculate it like this. They can be easily proved by just expanding the formula, and you can see it can be easily proved. And what about having two variables? Here, for example, x plus y. Then it's possible to calculate it like this. The thing that usually students confuse is that, are these two equal? What do you think? Not necessarily, okay? So we should be careful. Not necessarily they are equal, okay? And we should again check whether these two x and y are related, independent or not. Okay, now what if I have only a constant? What's the expected value of this constant? For example, what's the expected value of 2? This one is exactly equal to 2. So expected value of c, any constant number, is equal to c. I think I've covered the things that you should know. And also here in this formula, it makes sense now because you can bring out the multiplication easily because of what I said here. and you can separate the variables because of this part. Okay, so this formula makes sense. These things makes your calculations much easier, so they are nice to know. So what about expected value of a product? As we said, these two are not necessarily equal. Then we should check whether these two distributions are independent or not. So as you can see, it depends on this one. And whenever we are talking about calculating xy, so it's not easy as just multiplying these together all the time if they are not independent, then you can calculate them like this. So for case of continuous, I'm showing it here. For case of discrete, use summation, that's it. So what you do instead of, for example, what we have done for just expected value of x, we consider x here. Now we have x and y, so just consider x and y here, okay? But here we are dealing with two variables, so we should get double integral here. So dx, dy. Now this is a good time for you guys to go back and remind yourself about integrals, okay? For sure, I'm not going through very complicated ones because they have already evaluated you guys in calculus. So my goal is not to evaluate you how you calculate integrals, but the thing is that you should know it in order to solve some problems for a statistic. And that's why please go through them and remind yourself about it, not very complicated ones. And you will see also in our tutorials, we will practice together, and you will see I will show polynomials mostly, and they are very easy to calculate as double integral. Okay, what about variance and standard deviation? So expected value is related to central criteria. I will talk about it in details when we talk about median and mode as well. But you should know that when we talk about central criteria, it means that what's going on in the center, or I mean, what you expect from a data. Like, let's say we are talking about the height of students in a class. If the average of them is 162 centimeters, it means that this is the value that you usually expect if you randomly select someone. Of course, you have errors, and we will talk about also errors in details later, what we mean by that. But when we talk about variance, such criteria which shows that what's going on around your data, not in the center, how different are your data from the center? So this is a good way, this is a good criteria to consider. Like if I say in one class, the variance is small, and the average is 162 centimeters. So you understand that most of the students in the class, most probably they have height very similar to 162. One student 167, the other one 170. But in another class, if I say the variance is very high, so you may have some students which are very tall or very short, then which can totally affect the calculation of the variance. You will get much bigger comparing to the first class. So variance is very important, and we will practice it together. And also in the practical assignment, you will see it in practice how we deal with that. But anyway, how to calculate it? Like how different are the data from the center? So we are talking about the center, which is related to expected value. So I can show expected value like this, remember from the previous slide. Both of them can be used, okay. And later I will show that mu and x bar, there are two different things about population samples. We will talk about it in details as well. So when I want to calculate it, I should calculate this expected value, the differences from the center. So you power it by 2 so that at the end you will get a positive value. So when you want to calculate that, it's easier to consider this formula for your calculations. Of course, it's easy also to use this one for a small number of data, but when you have the information about each one of your attributes, And by the way, I should also talk about attributes later, remember this. And we will easily deal with it in terms of calculation by using this formula. It means that calculate this one, you already know it from the previous slides. I already told you here. Yes, you know how to calculate it, and we will practice it in tutorials, of course. And here, just calculate mean of the, expected value of the data and power it by 2. These two are different, okay? Be careful. I can also show it like this. Expected value of x power 2 minus expected value of x power 2. Okay, these two are different. So ex is equal to mu, okay? And for calculating a standard deviation is the square root of variance. And you can show it by sigma. For variance, you show it by sigma power 2. And why we need a standard deviation if we have already defined variance as a criteria to show how much the data are distributed around the expected value? We do that because in the calculation of variance here, we powered everything, the differences by 2. So here we try to make it as a similar unit to what we have as expected value. So a standard deviation, usually some statisticians prefer that comparing to variance because of that. But anyway, their nature is the same. By looking at either of them, we understand what's going on in the data, and you can compare it with other data and then say, for example, my class has less or bigger variance. Okay, what about covariance? So not always we are dealing with one variable, as you notice, and we keep practicing with two variables as examples. We can even expand it. But now let's say we have two variables and I'm interested to know how these data are differing from the center, and at the same time, what's the effect on one another. So in that scenario, we use covariance. And you can use this formula for that. So expected value of xy minus this multiplication of these two. You see, you consider the difference for each of them. Now, let's see if I want to compare covariance with variance from here so you have better understanding about these two. If I want to calculate variance of x, this is exactly equal to covariance of x. So covariance was actually the general format of variance. Now, if I'm comparing one distribution to itself, so I'm talking about just one set of data for one specific attribute. So in that case, you will reach exactly the same formula as before. So instead of y, just put x. What happens? So you write here x multiply x minus ex multiply ex. So what you will have is exactly the same formula for variance. So as you can see, they are not different in that case. So it is the specific case for variance that we are comparing it with itself. So ex power it by 2. The exact same formula that I've shown you here. Okay, about these two, I want to talk briefly because first you should know about the stochastic processes. Today, we talked about many things that will make sense in the future because we will keep talking about them in details. But anyway, we should start from a point. So we try to start it from these slides and also deal with probability distribution and what are discrete ones specifically. And we will practice with discrete and continuous distributions in the next 2 weeks more. So here, we should also know about stochastic processes, which we have also recorded ones for that. And here, let's talk about auto covariance and cross covariance very briefly. So later, when you watch the video related to stochastic processes, it's not a bad idea to take a look at this one, and it makes more sense. Now, here for the case of autocovariance, we are considering just one variable, and we compare it with itself. But this is different from variance. Now here, we are talking about the states. These parts, they are the states, like for example, x1, x2, and so on. Now we consider one of them and we compare it to, for example, what happens after n steps later. And again, assume that we go n step forward after each one. So let's say, let me show it here for better understanding. So x3, x4, x5. Let's say k here that we showed here is 1. Then my steps that I want to consider, as we call them lags, then is 2. Then I compare this one with this one. Then again, when I go forward, I compare this one with this one. And then when you do that, you will find a very interesting value that it shows you that what's the auto covariance in this data based on your stochastic process. And it gives very good information. And about 2 different variables. Also, we can have similar thing, but here, as you can see, the state is fixed. They are exactly the same when you fix it here. And of course, you can, by changing k, calculate for all of them. As you can see here, I did it for x1, x2, and so on. You can also change the number of k and calculate all of them. Unfortunately, in the future, you will have access to software, so easily you can calculate for all the possible steps. All right, let's finish the lecture with this slide, which is very important, correlation. And we can show the correlation coefficient, as we call it, by this notation, rho. The correlation between x and y variable, random variables. So to calculate this one, we consider both covariance and variances, you see. So covariance divided by the square root of multiplication of marginal variances. This is the way to calculate the correlation. And why do we need that? Why this is important? Because this coefficient shows us that whether 2 random variables are related to each other or not. And if they are, how much and how? So, and by how, I mean, for example, is it negative or positive? And the values that you can get is in this interval, -1 to 1. Let's say, for example, the value you get is close to 0. Somewhere around 0. For example, let's say 0.1. If this is the case, it shows that x and y are not that much related. So maybe not at all. And usually we have different threshold to decide for it, and based on the topic, it's different. For example, in psychological systems, even when we get 40%, we get excited. We say, okay, maybe they are related. But it really depends on the topic. And sometimes even 60% is not enough to say these two are related. It depends on the topic. And when you get closer to 1, let's say, for example, 80%, it means that x and y are related and they are positively related. It means that if you increase the value of x, you expect that y will be increased as well, okay? So if, for example, x can get value like 20, 23, 25, and for y we have 101, 105. So this is what you expect. Like if this is 20, then this is 101. Then when you change the value to 23, then you should have increase in y. And as much as this row is bigger and bigger, it depends how much, for example, it differs from this one. If this is 3, then maybe this one should be much more than, for example, 4 units, could be 125, for example. It depends on the value. And of course, they are not 100% accurate. Sometimes we have outliers, and we will talk about it in details when we talk about whisker plot. And okay, so for -1, what about that? It means that when you increase, for example, x, it's vice versa. You expect that the values of y increases. So they are negatively related to each other. For example, -80%, it means that they are highly related, but negatively, okay? So rho is very important for us, this correlation coefficient. And that's why please pay attention to it, and we will practice it a lot during our tutorial, and also in the next sessions we will deal with that again and again. Okay guys, I hope this lecture was useful for you, and please watch the tutorials also from the beginning to the end, and this lecture will make more sense as soon as you watch them. See you guys.